if you are going to compute by brute force approach, what will you do? The GCD of two integers can be at most what? GCD of two integers can be at most the minimum of m and n. It cannot be more than that. What do you mean by GCD? GCD is greatest common divisor. So what does it mean? The largest integer that can divide both m and n is the remainder of 0, right? So if you have, for example, the GCD of 120, 45, the largest integer that can divide both of them, the remainder 0, cannot be more than 45, right? The minimum of 120 and 45 has to be less than the minimum of the 2, right?
So I was...
Yeah. So if you do a kind of brute force approach, what would you do to determine the GCD from the programming class? Start from 1 and go all the way to the minimum, in this case 45, and see what integers could divide both 120 and 45, right? And keep track of the largest integer that can divide both, right? And make it 45, and then print out one of the largest integer that can divide both of them as the GCD, right? So you will do in this case 45 divisions, right? Because not 45, 90 actually. You have to divide the root indexes I, but I ranges from 1 to 45. You have to divide both 120 by I and 45 by I and get the remainder and so on. So you have to do 2 times the minimum of m and n, that many divisions. So as an optimization approach, this Euclid gave us this theorem which we can prove, and we do in the algorithm as for that. But here we just use the kind of a formula is the GCD of m on n comma m mod n. Okay. So now this holds good for any m and n, but you know, if m is equal to n, then GCD is the same, right? If m and n are the same integers, then the GCD is the integer itself, right? So if you want to find the GCD of 5 comma 5, it is the same, right? So we always work with something in this case, in general, say m, one integer is greater than the other integer, right? So now this helps basically to reduce the magnitude of the thing. Why? If you apply, for example, GCD of 120 and 45, according to this formula, basically m and n takes up the space of m, and the other one is 120 on 45.
30.
30, right? So you see there's a reduction in the magnitude. So instead of working with 120 and 45, we are working with 145 and 30. And repeatedly applying here. Now so far you did how many divisions? Just one division to compute this remainder, right? We didn't do any other division. And then this is GCD of 30 comma 30 mod, so 45 mod 30. So this is another division. What is this?
15.
15. And then GCD of, this is 15 comma 30 mod 15. What is that? 30 mod 15 is?
0.
And I think I told already there's a formula. So you have GCD of 15 comma 0. 0 to be divided by any integer and the remainder is 0, right? 0 divided by 15, the remainder is 0. 0 divided by 100, the remainder is 0. So any integer could, 0 divided by any integer, the remainder is 0, right? So the GCD of 15 comma 0 is what?
0.
15, right?
Oh, the greatest number. Okay, yeah.
Okay. So if you see there, I have written GCD of anything, k comma 0 is k. Alright? So if you count the number of divisions, you do 3 divisions here rather than 90 divisions. So this is the optimization. Okay? So from a programming implementation point of view. Now, what we are interested is a specific property of integers. You know what is a prime integer, right? When do you say an integer is prime?
Like 7, 1, and 3.
Yeah.
Like 3, 1, and 7.
Yeah, so if an integer is prime, if it can be divided only by itself,
Oh,
of course
1.
1,
Okay.
the remainder is being 0. If you divide that by any other integer, you don't get the remainder to be 0. Right? So all even numbers are prime or not.
Not.
They are not prime numbers because every even number is to be divided by 2. Then you get a remainder of 0. Right? So only for odd integers to be prime. Okay, so there is now something also called relatively prime. Right? So two integers are said to be relatively prime. Okay, so again n and m and n are said to be relatively prime if the GCD is 1. And this is what we are going to use in the interest for that. Okay, so they themselves need not be prime. Okay, so for example, GCD of say 24 and let's see, what else do I have? 53, but even you can have 53 and 30. If you do the math, okay, you get it to be 30 comma 53 mod is 23 and then what? You do 7 and then you do GCD of 7 comma 23 mod 7 is 2. Then what is that? GCD of 7 comma 2 is 2 comma 7 mod 2. What is 7 mod 2? 1. You can do one more step. 2 comma 1 is 1 comma 2 mod 1. 2 mod 1 is 0. Right? So eventually you get all the way to the second integer being 0 and you get 1. So you see here 30 is not prime, right? And 53 is prime, but in some cases, well, if there are two even integers, they cannot be relatively prime. Why? The divisor is at least 2, right? So one has to be odd, right? So you see that even though 30 is not prime, the GCD of these two integers is 1. So then these two integers are said to be relatively prime. Okay, so later in this, now we will look at, we'll just say, consider two integers which are relatively prime, but that this is what I mean. Okay, and sometimes you may have to test for relatively prime. Okay, so we have to go through this to do that. Alright. So given that, let's deviate a little bit and then we'll come back to this thing. We are looking at this modular arithmetic, right? And so when I say something class modulo, say 10, it means what? We are going to work with only integers between 0 to 9. Okay? Modulo 17 means you are going to work only with integers 0 to 16. So anything from 0 to 1 less than that integer, right? So everything else will be mapped to that. So for example, in this case, if you have say 35, 35 is equivalent to what? You want to find the equivalency, 35 mod 17 is 18, right? And then 18 is still greater than 16. So, which means we can say 35 is equal.
35 mod 17 is 1.
Oh, yeah. Right? So this is 1. Yes, that means it's a fraction, not a division. Yeah, so 35 mod 17 is a 1. So 35 is equivalent to a 1. Right? So everything outside this range, even negative integers, we can pull them back to this range. Right? So everybody's clear on that? What is modular, class modulo, whatever the integer n is? So all the integers will be pulled between 0 to n minus 1. If you have class modulo n. Alright, so now what we are into, last time we saw about addition, subtraction, multiplication, everything. So now we will look at what's called multiplicative inverse. In the real number world, if you want to find the multiplicative inverse, what we mean? So for example, the multiplicative inverse of say 10, we say it is what? Something you multiply with such that the product is 1. Right? So that's what we mean by multiplicative inverse. So normally we say the inverse of that integer is the multiplicative inverse. So that is 1 over 10 is 1, right? Isn't it? Now here again, in the modular arithmetic, we don't work with fractions. We always work with the real integers, the whole numbers. So what we mean by modular multiplicative inverse is modular arithmetic context, right? So like as I have here, if you want to find the multiplicative inverse of 7 in the class modulo 15, what it means is, again, class modulo 15, you have only integers from 0 to 14, right? So one among those 15 integers, 0 to 14, if you multiply with 7, the product, again in the modulo 15 context, should be 1. So for example, what I mean is, 7 multiplied by 0 is 0, right? So 0 mod 15 is 0. So that's what I have here. Then 7 multiplied by 1 is 7, so 7 mod 15 is 7. Then 7 multiplied by 2 is 14, 14 mod 15 is 14. Then 7 multiplied by 3 is 21, 21 mod 15 is 6. Then 7 multiplied by 4, 28, 28 mod 15 is 28 mod 15 is what? 13, right? So you keep getting all the reminders. Only one integer, you get the reminder to be what? 1. Right? And if you see here, everything else is actually unique. This is a very interesting property, right? So you multiply 7 with every integer, including 7, you get unique numbers, 0 through 15, right? In the class model 15. And only one such integer, you get the product. Okay, so 7 multiplied by 13. Okay, so that's 91. Mod 15 is going to be 1. Right? So we say this 13 is the multiplicative inverse of 7. Right? So we say this 13 is the multiplicative inverse of 7 the class modulo 15. Okay, so you have to be specific on what class we are talking about. So similarly, we can say what? 7 is the multiplicative inverse of 13, vice versa. Right? So even in the regular situation, if 10 is if 1 over 10 is the multiplicative inverse of 10, the opposite is also true. 10 is the multiplicative inverse of 1 over 10. So similarly, if 13 is the multiplicative inverse of 7, the class modulo 15, 7 is the multiplicative inverse of 13. Okay? Because again, multiplication is commutative, right? 7 times 13 is the same as 13 times 7. Alright, so I have another example, multiplicative inverse of 9 in the class modulo 13. So basically 9 multiplied by something, okay, and the product mod 13 should be 1. Okay, so we keep doing this and we see 9 multiplied by 3 is 27, 27 mod 13 is 1. Okay? For any other integer, we don't get it to be 1. Now, so for smaller integers, we can work like this. So if you want to find for a larger integer, you have to, like for example, the class modulo 300, then you have to work with like 300 multiplications and see which integer you get a 1, right? So that's why we don't want to do that, and we want to use an algorithm that can help us to find the multiplicative inverse. Okay? And that's what is called the extended inverse algorithm to find the multiplicative inverse of one integer in the class modulo some other integer. Okay? Alright, so now let's come back to this. Now again, there's a property of GCD. There are two integers m and n. We can write m times x plus n times y is the GCD of n comma n, where x and y are also integers. And we can find this x and y, as we are going to do, using extended inverse algorithm. And the one we are going to be interested at is if m and n are relatively prime. So this is a general property. For any two integers m and n, we can find the x and y such that mx plus ny will be the GCD of n comma n. So again, we are going to just use this property. We are not going to prove anything here. And if, again, if m and n are relatively prime, we just saw the GCD of m and n will be 1, right? So the right hand side will be 1. So it's basically mx plus ny will be 1. So now we are going to find this x and y. And what are these x and y? You see, x is multiplied by m, right? So we call this x as the multiplicative inverse of m, the one which you are multiplying with. In the class modulo, the other one is n. Similarly, this y is the multiplicative inverse of n in the class modulo, the other integer n. Right? So mx plus ny, x is the multiplicative inverse of m that we multiply x with. In the class modulo the other integer n. Similarly, y is the multiplicative inverse of n in the class modulo m. Okay? So how are we going to do this? Okay, so this is very simple. You just have to focus and I'll go step by step. These are a couple of examples. Now, so again, just for simplicity, we assume m is greater than n. Again, if you work with two, the integers are the same, they are not relatively prime, right? Except if they are 1. So GCD of say 3 comma 3 is not 1. So always there will be an integer m greater than n, right? So when we talk about relatively prime. Alright. So let's say we want to find the multiplicative inverse of 30 modulo 53. Alright, so this is the kind of part of the RSA algorithm which we're going to see after this. We want to find the multiplicative inverse, and as you see here, as a first check, sometimes I may do by mistake, sometimes I want to test you whether you know the underlying property. What is the first thing you have to make sure before you really spend our time going through the algorithm?
The n has to be larger than m, or vice versa?
That doesn't matter. The larger of the two is m and the other one is n. But what is that we have to check whether they are relatively prime or not. Okay? Right. Then in this case they are relatively prime. So in general, first just make sure, and how do you make sure? Just go through the GCD formula repeatedly. Okay? Because if they are not relatively prime, you cannot find the multiplicative inverse. Okay, so as a practice, you could assume two integers which are not relatively prime and go over this algorithm, but you will not be able to find the multiplicative inverse. So first make sure they are relatively prime. Okay, so basically what it means is, at this stage here, we want to find the x and y such that 53x plus 30y is 1. So, as it is, given this statement, I want you to find the multiplicative inverse of 30 mod 53. right? So between x and y, which is where we are really interested at, x or y? Remember, the thing is mx plus ny is 1, and I said what? X is the multiplicative inverse of n modulo n, right? And y is the multiplicative inverse of n modulo n. So in this case, the larger one is m, so 53x plus 30y is 1. So we'll go through the algorithm, but eventually you need to know what is the multiplicative inverse of 30 modulo 53. So are we interested in x or y?
Why?
Y. Y.
Why?
Y is multiplied with 30, right? So by definition what it is? Y is the multiplicative inverse of to what it's multiplied, n, the class modulo m, right? So if you want to find the multiplicative inverse of 30, look where what you are multiplying with 30, y. So we are really interested in the value of y. Okay? You will be finding both x and y. So, but if I ask you a problem like this, you have to pick the value of y. You don't need to pick the value of x. But as we go through, we'll find both x and y. Alright? So keep this in mind. Alright, so the way we'll do this is, we'll go through a kind of a table. You just have to have one table when you do the exam, but just illustrate I have multiple instance of it. Just go through one table, we'll go to the slide, the board also. But the slide are used different colors, so that's easy to look at first. So this is how we start with kind of initialization. So it's always the same. You have four integers a, q, x and y, and then m and n, 53, 30, the two integers. M is 53, n is 30, and this is also fixed, 1, 0, 0, 1. What this eventually is, x and y, we are going to find the eventual values of x and y, but this is a kind of initialization setup. Okay? And this q actually stands for quotient, and a is actually stands for reminder, as we go through the rest of the equations. But this is a kind of initialization. And the first value of q is nothing. So what we'll do is, in every iteration, we'll go through in iterations. Okay? So this is initialization. And then in every iteration, what we are going to fill up is this. We are going to fill up, so for example, we have a, q, x and y, and let's say you have 53, 30, this m and n. So this is what we have. So in every iteration, we are going to fill up the q, the earlier row, because you see here 0 and 1 are already here. So we are going to find this entry and these three entries. Right? So once we find these four, the next iteration, we will find this and these three. And we keep going. Okay, so that is how we do the extended integral algorithm. And how do we do that? So let's see the first iteration. So the first we have to find the quotient, which is this thing. So q, the quotient is nothing but when 53 divided by 30, what is the quotient? 1, right? Isn't it? So if you use a calculator for larger integers, just divide 53 by 30, whatever is the quotient, you get 53 over 30, 1 point something, so that this is the quotient. The remaining thing is the remainder. Right? And that remainder is actually 23. Okay? 53 divided by 30, the quotient is 1, which is here, and the remainder is 23. Okay? So I write step by step. So this is 1 and then 23. So now we have to find this x and y values for this iteration. Now the way you are going to do that is, you take up the previous value of x, which is 0, multiply by the value of this quotient, which is 1. So it is 0 times 1, which is 0. And subtract whatever the product from the previous value of x, which is 1. So basically it is 1 minus 0 times 1, which is 1. Okay? So if I want to find this, entry, all I have to do is go 2 entries above this. 2 entries above this is this 1. This 1 minus the just immediate entry, top entry, which is 0 times the quotient value. Okay? So if you look at from the algorithm point of view, if you are comfortable with that, so x of k is x of k minus 2 minus the product q of k minus 1 times x of k minus 1. So 2 entries above the current entry minus the product of the quotient and the x value, the immediate top. Okay, so 1 minus this. Same thing for y. What will you do? 0. 2 entries above this entry is 0 minus what? The quotient again 1 times this 1. So 0 minus 1 times 1 is 1. So 0 minus 1 is negative 1. Right? So that's all it is. So you repeat this for every iteration until we can stop. Right? Here? Alright, so we divide what? 53 divided by 30, the quotient is 1. Right? So Q stands for quotient. And then this is the remainder. Right? So you want to find this x and y. How you find x? So you want to find this entry. So go 2 entries above this. 2 entries above this is 1. So 1 minus the product of the quotient in the previous entry times the x value in the previous entry, which is 0. So 1 minus 1 times 0. What is 1 minus 1 times 0? 1 minus 0, which is 1. So this is what is 1. Okay? Similarly, if you want to find this, the y, it's going to be what?
0 times
0, this 0 minus this 1 times this 1, which is the quotient. So it is 0 minus 1, negative 1.
Okay.
So this is going to be negative 1. 2 entries above, and then always the quotient is like a pivot. That quotient times x and then the y. Okay? Now, so this is what you have at the end of the first iteration. Repeat this. So now your m and n are like 30 and 23. So now to find this quotient, you have to do what? 30 divided by 23. 30 divided by 23, the quotient is 1. That's what I have here. And the remainder is 7. Okay? 30 divided by 23, the remainder is 7. So now tell me what will be x and y. How do you find them?
Go 2 above.
2 above this entry is what?
0
0
minus the quote.
Times
The
that
quotient
1.
times the immediate top is 1.
Right.
So it is 0 minus
1.
1 times 1, which is 1, right? So let me fill it up and we will do it here. So what is that we have here? This is 1 and then this is the quotient, reminder. So this is again 1, this is 7. So what is this? This 0. The 0 minus this 1 times 1 is going to be negative 1. Here? Here?
Do it one more time, Dr. Mayor.
Okay, so I want to find this. So I want to find this. Let me remove all these things. I want to find this. So 2 entries above this is this 0. Then what is this? Minus, this is going to be the quotient times the immediate top is this 1.
Okay.
So 0 minus 1 times 1 is negative 1. In the same way, tell me what should be this y value.
Go up to.
1,
So it's gonna be
1 minus 0,
minus 1.
minus 1. Go back to the quotient.
1 times 1.
1 times negative 1, right? This 1 minus 1 times negative 1,
Okay.
right? What is this?
1 times 2.
One,
2.
this is 1 minus minus 1,
Two.
so it is 2. Alright, so you have to be careful. So that's going to be 2. So this is what you have, and you want to keep going. So 23 and 7. So if you divide, what is the quotient and remainder? 3 is the quotient and 2 is the remainder. So you have 3 as the quotient and 2 as the remainder. And then fill up the x and y. So this is 2. So 3 and 2, right? So what should be these 2?
It's going to be negative. It'd be, you said negative 1?
This is a 1
Okay, 1 times minus 3?
minus
The 3?
what are two things you multiply? Always the quotient.
Mm-hmm.
3 times
Negative.
the immediate top x value, which is negative 1. Right? So it's going to be 1 minus 3 times negative 1 is negative 3, which is 4. Right? Any questions? So now tell me, you have to tell me what should be the y.